Hello, my name is Ashwarya Pillai. In this video on reduction potentials, you are going to learn how to calculate the cell potential of a redox reaction. In order to determine whether a reaction is spontaneous or non-spontaneous, you must either know the value of the cell potential or the change in Gibbs free energy. The value of the cell potential can be found by adding the reduction potential and the oxidation potentials together. This is because the cell potential represents the energy per unit charge that is available from the redox reactions. Since the reduction potential indicates how much usable energy is added if a chemical species gets reduced, and the oxidation potential indicates how much usable energy is added if a chemical species gets oxidized, the cell potential therefore reveals how much usable energy is available from the overall reaction. So, if you are given an overall equation for a redox reaction, you can begin by splitting the equation into a reduction half reaction and an oxidation half reaction. Then, you can use a table of standard reduction potentials to locate the relevant reduction and oxidation potentials. For a spontaneous reaction, the reduction half reaction is the one with the higher reduction potential. In this case, that would be copper. Since copper is the entity that is actually being reduced in the reaction shown on the previous page, we therefore know that it is a spontaneous reaction. To find the oxidation potential, we take the reduction potential for zinc and flip the sign to get positive 0.763 volts. Finally, we can go ahead and add up our oxidation and reduction potentials to determine that the cell potential is 1.1 volts. Thus, our reaction is spontaneous and will run without any external input. Let's give this a try with a few examples. Our first question asks you to calculate the cell potential and then determine if it is a spontaneous reaction. As before, we can begin by breaking the reaction down into half reactions and using the table to find the corresponding reduction potentials. Since zinc is again being oxidized according to the reaction equation, flip the sign to find the oxidation potential. Then, add them together to get a cell potential of negative 0.147 volts. Since the cell potential is negative, this must be a non-spontaneous equation. This means that while it would run spontaneously towards the left, aka towards the reactants, in order to get it to run toward the right, you would have to add energy to the system. Looking at our second example, you can again start by breaking the reaction down into half reactions and using the table to find the corresponding reduction potentials. As per the reaction equation, copper is being reduced while hydrogen is being oxidized. However, hydrogen is kind of a unique case. Remember that standard reduction potentials are measured with respect to a standard hydrogen electrode, which is assigned a value of 0 volts. Thus, the reduction potential is the same as the oxidation potential for hydrogen. Adding them together gives a cell potential of 0.337 volts, which is positive and therefore spontaneous. The third example presents the reaction written in shorthand notation for an electrochemical cell. Within this notation, the left represents the anode and the right represents the cathode. Since oxidation occurs at the anode, think anox, zinc is being oxidized. Similarly, since reduction occurs at the cathode, think red cat, copper is being reduced. After finding the reduction potentials, we again flip the sign for zinc's reduction potential to get the oxidation potential, and add them together to get a cell potential of 1.1 volts. Since it is positive, this reaction is spontaneous.